Welcome to EDU World Space.
Hello, today we're going to be discussing why many of the oxides of nitrogen have positive values for the standard free energy formation. And that's going to be using NO as an example. So why is this the case? Okay, so in the problem we're given that that we're supposed to explain why the standard free energy of formation it has positive values for nitrogen oxides. So immediately I would write down the Gibbs free energy formula, which goes something like this. Delta G, Gibbs free energy, equals delta H minus T, temperature, delta S. And let me write this in enthalpy for heat, red for heat, and entropy is delta S, entropy. So change in enthalpy before and after the reaction, and change in entropy before and after reaction. And we have nitrogen over here. Nitrogen. And this is horrible. Oh. We have nitrogen atom. And that's usually as N2, that's the before. It reacts with oxygen, it's gaseous nitrogen, G. And after, it's going to turn into some N oxide. And that's going to be also gaseous, and that's going to be the after. And I'm not writing a formula because there should be I'm just writing a conversion from N2 to NO. No chemical formulas here. But this is sufficient. This writing this and writing the conversion is sufficient to figure out why delta G is positive. Why is delta G positive for nitrogen oxides? And there's a reason for that. If we look at a bond energy chart, we can see that the NN bond, this bond over here, this is the NN bond. It has a energy of bond enthalpy rather. It's essentially the energy of the bond, how strong the bond is. It is 163 kilojoule per mole. And the NO energies, bond energy, that's going to be much higher, 201. And we're considering NO as an example, but there are other oxides such as NF, NBr, and nitrogen bromine. It's 201 kilojoules, my bad. 201 kilojoules per mole. 201 kilojoules per mole, and without me explaining it, you can see that this is the before, and the after. And as I said, without explaining it, you can see that clearly this is a smaller number than 201. Okay, my bad. It's not drawing here. All right, so you see the number 201 and you see 163. And why that is, we can just make some space since you understand this. The bond energy just gives it away. And remember that for every N2 or for every 1 NN bond, we're producing 2 NOs. And this is again for this is for the NO, the nitrogen oxide, but there are, as I said, many other oxides that one should consider. So this is for NO, and it forms 2 because there's 2 nitrogen, and of course there's the oxygen bond energy, which is quite low as well, since diatomic bond energies are pretty low, 146 kilojoules per mole. So adding 146 and 163, we place in about 300, something like that. That's before. And after, we place in something like 402 kilojoules per mole. And there's a little bit of nuance here. One could argue, or as a challenge, your teacher could or professor could easily tell you that the entropy is higher, and therefore, assuming constant temperature, the entropy is going to be higher and subtract from the positive delta H over here, which is about 100, about roughly 100 kilojoules per mole. You will have to notice that the enthalpy is much higher. It's going to overcome this small entropical increase, but that is still significant. That as we split N2, remember we're splitting. Oh, my bad. The entropic increase is not very big because even though we're going from N2, my bad, to and O2 to NO and NO, so 2 molecules to 2 molecules versus like if you're splitting a hydrocarbon, that's going to be so much carbon. Carbon dioxide is going to be maybe you have one hydrocarbon, one O2, and splitting that into like 14. My bad. 14. It's not writing. 14 different additional molecules. The entropic increase is not very big here because we're only going from 2 to 2, not 2 to 14. So if your teacher does challenge you that the enthalpy is actually being decreased because of the entropy increase, that's actually a small difference that the entropical increase makes. So I hope that makes